All right. Welcome, everybody. Great
Hello,
to see
everyone.
so many of you guys. Yes. Also, there's a chat relay here. If you guys want to send your messages in, let us know that you guys are here. That would be great. Make sure you're sending it to chat relay on Zoom. Yay! People are saying hi.
Make sure that your name in chat relay isn't your real name.
Alrighty. While you guys are joining, we have a little question for you guys. So it's a very hypothetical thing, but imagine you were offered $1 million, but you're chased by a deadly bug for the rest of your life. And if that bug ever touches you, you go to jail for life. The question is, are you still going to take that $1 million? And if you do, what's your plan on keeping yourself safe?
Honestly, I wouldn't take it because the worry of being caught by the bug and spending the rest of my life in jail is going to occupy me a lot, and it's going to make me really nervous for the rest of my life.
Honestly, that's a really good point. I don't know if it's because we're old. We're not even that old. But originally I was like, $1 million. But now I'm like, stress causes health problems. And those health problems might might cost you more than $1 million.
Oh, Alex Y says, how fast is the bug? Is it immortal? And you're not given any of this information before you take the deal. So you have to go into it completely blind. It could be
So
super slow or it could be super fast. You don't know.
let's say that it's like kind of slow, but it's immortal. It can travel anywhere, so like across the ocean, and it can bite through metal if you try to put it in a cage. So it can always go towards you. But yeah, no, it never dies. You kind
You
of just
can't bug spray it, unfortunately.
raid.
If that did work, I'd take the million in a heartbeat. But
Yeah,
unfortunately, nothing is that easy in life.
that's true. No, nothing comes that easy. Helen wouldn't. All right. Give it to a person who likes to eat insects. This is a good question. Well, obviously it has to survive stomach acid, but would the person just
Maybe
keep eating it?
maybe if they kept eating it, then it wouldn't be able to catch you because once the bug escaped, it would just get eaten again.
So what if you pay somebody to eat the bug for the rest of your lifetime, and the wage you pay them is like 100,000, so you still have 900,000 to use.
So just a lump sum of 100,000.
Maybe, or maybe you do it at a constant rate. I don't know. I assume it goes towards you at a constant rate, so you can't trap it. Maybe you could trap it, but like if you put it in a cage, it can eat through the material or something. So like slows down a little bit.
Wait, actually, Helen, this is an interesting hypothetical. If you had the opportunity to get like $100,000 to eat a bug for the rest of your life, would you take it?
That's funny. We're just branching off more and more hypotheticals. Now it's like, if there's an answer yes to that one, we might answer yes to this one. It's changing the problem. Same idea, but different question.
Reducing a problem to a different problem.
Perhaps a strategy we'll be using.
Well, we'll see if it does get used. But as for the $100,000 to eat a bug for the rest of my life, that I probably would take because eating a bug, although it might be kind of inconvenient, it's just a bug. And I'm not that scared of bugs. And getting $100,000 for getting $100,000 is enough money for that to be worth it for me personally.
Yeah, I agree. Absolutely. I mean, some people already do eat bugs. It's like sometimes used as a snack for protein now. I was at a chemistry convention and they just had these bugs. They're like, oh, new way to get protein. And then my chemistry teacher is also there, and she loves eating weird things, including like paper sometimes. And so, anyways, she just took the bug and was like, very crunchy, doesn't taste that good.
Well, yeah, Matthew, if you could run at the same speed as the bug, sure, you could escape the bug, but you have to go to sleep eventually, right? So you actually have to run at twice the speed of the bug so that the bug can't catch up to you while you're asleep.
You should just fly to a different continent at that point. Maybe Australia, because today we're doing the Math Kangaroo live solve, and we're going to be going over the 9th through 10th grade competition. We've picked 10 problems, and Vince and I are going to be live solving them. So we haven't done them before. Just going to take a blind look at them. So as you guys know, I'm already joined by Vincent today. Vincent's super cool. So not only is Vincent a mopper, which is basically a summer camp for 60 students, the best 60 math students in the entire nation. They go to a summer camp. And not only did Vincent do that, but he's also a silver medalist for the USAMO, which again, like basically the top math competition in the United States. And on top of that, Vincent really likes Rubik's Cubes. So all around, super cool.
We also have Eddie, who's the Math Counts Ohio State champion. He qualified for Amy, and he likes learning languages.
Awesome. So without further ado, Vincent, do you want to take the first problem?
All right. Each year, the third Thursday in March is named Kangaroo Day. The dates of Kangaroo Day are shown below with one error. Which date is wrong? Is it March 17th, 2022, March 16th, 2023, March 14th, 2024, March 20th, 2025, or March 19th, 2026?
As always, if you guys have ideas, you can drop it down in chat. But let us know how you guys are doing the problem. Oh, do you know the solutions to the problem before you do them? No. So the idea is Vincent and I are just going to look at the problem and we're going to walk you through our thought process. How would we solve this problem?
Well, Matt C says doomsday algorithm. What's the doomsday algorithm? One thing I see is that 2024 is a leap year, so we have to keep that into account. So there's 365 days in a year, except for leap years where there's 366. Oh, it's an algorithm to calculate dates. Seems interesting. So if it's a non-leap year, then there will be 365 days, which is 52 times 7 plus 1. And you can verify this by just multiplying it out. 52 times 7, 14, and then 35 plus 1, 364. Add 1 is 365. So that means a full year has 52 full weeks and then just a random extra day. So that means whatever date it is on that year. So if March 17th, 2022 was a Thursday, then March 17th, 2023 would be the next day. And then when it's a leap year, then it goes forward by 2 days. So yeah, it is a good application of modular arithmetic. But hold on, I just noticed this one, March 14th, 2024. There's no way it can actually be the third Thursday in March because there's not actually enough days to go around. So let's say if it was the third Thursday in March, then what would be the first Thursday in March? Well, the first Thursday in March and the third Thursday in March are 14 days apart. They're 2 weeks apart. So that's 14 days. So the first Thursday in March has to be 14 days before that, which means it would have to be March 0. And that doesn't exist. So basically, we said that if March 14th was the third Thursday in March, then the first Thursday in March would have to be March 0. So therefore, yeah, exactly. It could only be the second Thursday, not the third Thursday. So as Eddie has on his screen, the first day, if Thursday was the first, if the first day of the month was a Thursday, that's the earliest it can be. Then the third Thursday of a month, the earliest that can be is the 15th. So it can't be the 14th. no matter how the days happen to fall. And so this is our answer.
Yeah, that's a really good note. So the thing is, we might be tempted to look at algorithms or different ways to grind it out. But the thing is, this is number one. So obviously, this is not a guaranteed strategy, but I feel like you should be like, there's probably a really fast way to do this because it's number one. They wouldn't put it number one if there wasn't some like really easy way to look at it. I used this logic for one of the AMCs actually, and it kind of worked. It was the one where it says which one is prime, how many of them are prime, and I was like, it has to be zero because the problem is really early on. So basically the logic is, if this is the first question on the test, it's probably going to be easy. And so by finding some sort of trick like this, where it's like, wait, it's impossible for the 14th of a month to be the third day of a week. Because, whatever the first of the month is, the third time that happens is the 15th. So that 14th is impossible. Cool. So basically, always try to look at the answer choices, look at some shortcuts you might be able to take before you keep going with the problem. All right. So we have a floor plan looking thing here, and on to number 4. We have 6 rectangles, and they're arranged as shown. The top left-hand rectangle has a height of 6 centimeters. We're all in centimeters here. The numbers within the rectangles, so this 18, this 32, 48, all the numbers within the rectangles indicate their areas in square centimeters. What is the height of the bottom right hand? Oh, bottom right hand, this one. Bottom right-handed rectangle. So we're looking for this height right there. So we have these options here. We could use the answers to our advantage. I mean, like for example, right away, it didn't tell you it's drawn to scale. So it didn't say it's not drawn to scale. It didn't tell you it's drawn to scale. Just looking at it, this height is shorter than this. So I'm kind of tempted to say it's either A or B. And the fact that 30 doesn't divide 4 nicely makes me want to say it's 5. But this is just pure guessing. Let's just figure it out. So since these are all rectangles, yes. Okay, so Luke has a lot of the calculations. So because this rectangle here is area 18 and one side is 6, we know the other side is a 3 because 6 times 3 is 18. And then Luke says the bottom left, this length is also 3. So this is going to be a 3 by 4. So this height is going to be 4, right? Which means this height is also 4. And since this is a square with area 16, it's going to be a 4 by 4. And then we could keep going. So this is height 8 because 8 times 4 is 32. And then finally, since 8 and another side make 48, it's going to be 8 times 6. 8 times 6 gives me 48. And then finally, 6 times this height gives me 30. So I was completely guessing earlier just based off of, random logic, but it turns out it is 5. And a lot of you guys are getting 5 as well. Helen, Rithvik, all saying 5. And now that we've confirmed going through the kind of like a maze, we know for sure that the answer is 5 centimeters. Cool.
Yeah, it really is a maze. You start out from the top left and you're just like snaking around. But without further ado, let's get to the next problem. We started with problem 1, then we did problem 4. So what do you think is going to be the next problem? It is problem 7. So do you guys see the pattern? But if you guys see the pattern, feel free to put it into chat. But let's look at it. In a jazz band, one person plays the saxophone, another person plays the trumpet, and a third person sings. And they are all the same age. There are 3 more members of the jazz band who are 19, 20, and 21 years old. The average age of the jazz band is 21. And they want us to find how old is Eliana. So let's try to use the information that we're given. So if the average age is 21, then that means the sum of their ages divided by the number of members has to equal 21. So let's count the number of members. We've got 1, 2, and 3, and 3 more. So that's a total of 6. So now let's look at their ages. The three that we're given are 19, 20, and 21. And then we don't know the other three ages, but we do know that they're all the same. So let's just call them all X. And we know that the sum divided by 6 equals 21. And yeah, Luke has the right idea here. So we'll multiply both sides by 6. And now we get 126 equals 19 plus 20 plus 21 plus 3 times x. And then we'll subtract all of these numbers from both sides. Minus 19, minus 20, minus 21. And when we do the subtraction, that gives us 66 equals 3 times x. So 3 times what is 66? That would be 22. So just by using some algebra, we can find that Eliana is 22 years old.
Cool. So that was really straightforward algebra, grinding it out, just knowing what an average means, right? Average is the sum divided by the number of its members. Another way to look at it, if you don't want to add up all the 6 numbers, is if the average age of the jazz band is 21, that's saying that the total years of age would be the exact same had all the members been age 21. That's another way of looking at an average, right? It's basically saying if everybody is 21, same total years of age across all of them. So let's compare them. We know that this sum is equal to this sum. So the 19-year-old is 2 years below the average. The 20-year-old is 1 year below the average. And then the 21-year-old is exactly on the average. So far, we're 3 years below the average. But we want to be exactly on the average. So in order to do that, while also keeping in mind that these 3 have to be the exact same age, we know that all of these have to be 1 year above the average, which is another way of saying, wait, if all of them are 1 year above the average, they're all 22. So 2 ways of looking at it.
Yeah, that was a really nice way of looking at it. That doesn't require as much computation. So let's go to the next problem now.
All right, so we have a little kangaroo, and it chose, I wrote it as being chased, I don't know why. It chose a special number, and then the kangaroo gets the same result when she subtracts 1/10 from her number as she does when she multiplies it by 1/10. What's her number? Okay, well, another thing, really nice part about multiple choice is that if you have no idea, there you have it. There's 5 choices. You can see which one matches. But imagine if there weren't, let's see how we would try and tackle the problem. So special number, right? It's really vague. We don't know what it is. So that's our cue for, we should set a variable. So we're going to call this special number. Do you guys want to put a variable in chat? What variable you guys want to use? Uh-oh, I missed it. What do you guys want to call it? I mean, obviously we would go with X normally, but all right, Matt was first. Matt said N. I would have picked K, but democracy wins. All right, so we pick N. The number's N, probably for number. And so she gets the same result when she subtracts 1/10. So subtracting 1/10 from her number would look like N minus 1/10. And if it's the same result, that means it's equivalent to if she had multiplied it by 1/10. If she had taken N and multiplied it by 1/10. Now we just solve. So yeah, Ethan wrote it out. So 1/10 is the same thing as 0.1. So Ethan says X minus 0.1 is the same thing as X times 0.1. And at this point, I don't see any other way to do it other than combining like terms. I actually will write it the way Ethan did. Oh well, Matt put it in fractions right there. Actually, you guys have a lot of great stuff in chat. I'm going to go with the decimal way because I saw that first, but absolutely. You can look at the fractions in terms of denominator 10, which in case you can multiply everything by 10, that might make it easier. But same equation. Now what we're going to do is subtract 0.1n from both sides. That way we get all the variables on one side. So if I subtract 0.1n from both sides, I'm going to get 0.9n minus 0.1 equals 0. In which case, n is equal to 0.1. Well, I skipped a step. 0.9n is equal to 0.1 after you add 0.1 to both sides. And then what you can do is just divide both sides by 0.9. I'm too lazy to rewrite it, so I'll just do that. And what's nice about 0.1 over 0.9 is that this is equal to 1/9. So after multiplying both top and bottom by 10. So we know that it's exactly what you guys are saying in chat. It's what Cubes has on screen right now. 1/9 E. Yeah, good job, Karsten.
Great. This seems like a pretty straightforward problem, but once we've solved it, it's really easy to check our work. So if we have extra time, we can just do that if we were taking it on a test. So let's see how we would do that. If the problem says that if we subtract a 10 and if we multiply it by a 10, we would get the same thing. So let's try that. Let's first multiply it by a 10. 1/9 times 1/10 equals 1 times 1 is 1. 9 times 10 is 90. Now let's subtract a 10th from 1/9. Let's see what we would get. Hopefully it's the same thing. If it wasn't, we'd have to go back and check our work. So 1/9 minus 1/10. Let's change these fractions to have common denominators. So 9 and 10, their least common multiple is 90. So we'll change this to 10 over 90 minus 9 over 90. 1/9 is 10 over 90 and 1/10 is 9 over 90. And when we subtract them, we do indeed get 1 over 90. So since these match, we can be confident that we got it right. So since we are done with that, let's move on to the next problem. The numbers from 1 through 6 are placed in the circles at the intersection of 3 rings. The position of number 6 is shown, and the sum of the numbers on each ring are the same. What number is placed in the circle with the question mark? Is it 1, 2, 3, 4, or 5? So in this one, the answer choices aren't really that useful. So let's try to use the information in the problem and try to figure it out from there. So one thing I see is, let's look at these 4, for example. These 4 spots have to add up to a certain number. What do we want to call that variable name? We used X and N, and I feel like using a different letter. It doesn't even have to be a letter. It could be a Greek letter or a shape maybe. No, don't choose a shape. But if you guys want to pick another letter, then put your suggestions in chat. Okay, Matt C says K, and since that was the one I said first, we'll go with it. So let's call this sum K. So the sum of the green circles is K. Now, what do we suppose that the sum of these ones are in red in terms of K? Well, that would just be the total sum minus the sum of the green ones. And the total sum is just 1 plus 2 plus 3 plus 4 plus 5 plus 6. So the sum of the red circles would be 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is 21, minus the sum of the green ones, which is K. So the sum of these red ones is 21 minus K. But what if we did that process? What if we did that process for a different set of 4 circles? Let's say we, instead of doing these green ones, let's say we did this one, this one, this one, and this one. Then we would deduce that using the same logic, this one and this one that I'm pointing to with the yellow arrows also add up to 21 minus K. And likewise, let me change to a different color. This one and this one would also add up to 21 minus K. But hold up, these pairs all add up to the same thing. And the sum of all of these pairs is just 21, the sum of every single cell. So if all 3 pairs add up to the same thing, and their sum is 21, then we can figure out the sum of each pair. That would just be 21 divided by 3, which is 7. And we're almost done. We know that this is a 6, and this one plus this one is 7. So what does this one have to be? 6 plus what is 7? Well, that would just be 1. So that's our answer.
Cool. So that's like a really nice way of using some logic to make the process easier. I think you might have been able to experiment around and see which ones work, but what Vincent did by pairing them up and realizing that every ring consists of 2 of these pairs, every pair has to be 7, which reminds me exactly of a die. So on a die, the rule is all the numbers on opposite sides have to add up to 7. So if I have 1 on this side, then the opposite side is a 6, and 3 and 4, etc., etc.
Wait, that actually means that if you have a die that satisfies that property, then the ring of numbers, like this one, the one on the back, and the one on the left, would all add to the same number because that's just this problem. So that's a pretty interesting application.
That's actually really cool. So we basically took this 3D shape and put it onto a graph with lines that is very 2D. So maybe we could ask Professor Lowe about graph theory because graph theory is all about, you know, I don't want to just say like lines and nodes, but it's obviously a lot more complicated than that. But if you take Module 3, you might actually know a little bit. Alrighty. So again, just using the pairs, exactly like a die, makes this problem a lot easier. Moving on. Unless, Vincent, do you have anything else for this problem?
No, I think everyone's ready to move on.
All right, Hamiltonian paths. That's a word that I do not know, and it might be graph theory. So you guys clearly know a lot more than I do. Alrighty. So now I always get the long word problems. In a team competition, there are 5 teams waiting to start. Each team consists of either only boys or only girls. The number of teams, sorry, I'm gonna interrupt this real quick. Remy says, can I see the work again? So this is actually being live streamed on YouTube, and I'm pretty sure when we're done, the recording will still be up there. So if there's anything you guys want to rewatch or go back and look at, you can head to, the channel name is called Daily Challenge with Po-Shen Low. I bet I can type that in chat right now. So head to Daily Challenge with Po-Shen Low, and then I bet you can find our live stream, and then there you can watch whatever you want, however many times you want. But obviously, if you guys are confused and we have on anything and we have extra time at the end, we can always go back and do some of the problems again. No worries. Thank you guys for asking questions. Okay, so again, team competition, 5 teams waiting to start. Each team consists of only boys or only girls, and the number of team members are 9, 15, 17, 19, and 21. The first thing that I see right now when I look at that is they're all odd numbers. That's a little odd. After all members of the first team have started, the number of girls who have not started yet is 3 times the number of boys who have not started. Sorry, what? After all members of the first team have started, the number of girls who have not started yet is 3 times the number of boys who have not started yet. How many members are on the team that has already started? Okay, so basically, I'm going to take only this part and just redo and just let's make 5 circles. So we have a team of 9. Okay, it's way too big. A team of 9, a team of 15, a team of 17, a team of 19, a team of 21. And it's basically saying once one of the teams starts, so I'm going to take one of the teams out of the picture because out of the teams that haven't started, which remember, they're either all boys or all girls for each team, it says, let's, for example, say that these are the girls' teams and these are the boys' teams. All the girls' teams combined who haven't started are equal to 3 times the value of the boys' team that hasn't started. So we have to figure out which team to remove where it is possible to have some amount of remaining teams combined to be 3 times the ones that we didn't combine. So hopefully that makes sense. If not, I'll pull up the question again to review. Basically, the idea here is Yes, how to make the sum of three groups 3 times the other? Well, it doesn't have to be 3 technically. If you had, I don't know, say 21 plus, okay, that doesn't work. 21 plus 15, right? And then that is magically 3 times the other one. It doesn't have to be 3 groups, but I think the team that started can only have 9, 17, or 21 people. Ooh, Arjun, do you want to explain? That's a really nice observation. I want to see how you got that, because that is exactly what we want to look at right now. We want to narrow down some possibilities. And right away, you want the sum of the other 3 and the respective difference of the boy team to be 0. Yeah, that's another way to look at it as well. If you think about it like a balance, you want them like 3 times the boys and the amount of girls to even out. The way I want to think about it is, let's say that the girls team's left over. I was going to give it a variable, but we're going to say that's exactly 3 times the amount of boys left over. So wait, instead of separating them, let's think about them together as one big group, as the not started group. The fact that you can split it into a number that's 3 times the other number means that together, however many boys there are, in total, there are 4 times that, right? Because the amount of boys, right? I say this amount of boys, and there's 3 times the amount of girls who haven't started, which means combine them, it's going to be some multiple of 4. So you're saying out of these people, I take one of the teams out of the picture, I'm going to get something divisible by 4. Yes, exactly, Alex. The remaining sum must be divisible by 4. So we're going to first add up all the teams, and the way I'm going to do that is 9 plus 21 looks fun, and the rest are not that fun. So I'll do 17 plus 19. It's going to be 36. That's going to be 30. Then you add 15 to that. So that's 51. 30 plus 51 is equal to 81. So, oh, I see where the 1 mod 4 is coming from now. So 1 mod 4 is just a number that leaves a remainder 1 when divisible by 4, when divided by 4. So I want to subtract a number from 81, has to be one of these 5, such that it's divisible by 4. And the only numbers that happen to, basically, right now, if I were to divide this into groups of 4, I would have 1 person left over. It has remainder 1 when divided by 4, right? But 9 has that same property, remainder 1 when divided by 4. So does 17, so does 21. If I took 15, for example, I can't subtract that remainder 1 out. But yeah, exactly. We need a multiple of 4 when we subtract out one team. So we only keep the numbers that are 1 remainder 4, because it like takes away whole groups of 4s and gets rid of that extra remainder 1 for that from the 81. So we know it's either 9, 17, or 21. Carson says 21. As always, you guys can send your explanation chat how we get that. One way we could do this is literally just try. So like we had 81 people. So if I took away let's just go from smallest to greatest. 81 minus 9 is 72, right? If I have 72, that means the amount of girls left over is, well, let's divide into 4, because dividing by 4 gives us how many boys are left over, right? 72 divided by 4 is 18. So there's 18 boys left over, and 3 times as many girls. That's 54. Is there a way we can make 18 with our remaining numbers after getting rid of the 9 group? No. So we can't have that. What about for 17? For 17, 81 minus 17 is, one moment, 81 minus 17 is going to give us 64. So that means the boys, is that divided by 4? So 16 boys. Is there a way to make 16 boys? No. Yes. Okay, so Arjun's saying it can't be 9 or 17 because the sum of the remaining teams is an even multiple of 4. So the reason why we're looking at even multiples of 4 is after you divide out the 4, you get an even number. And the only way I can get an even number is if I add 2 of these, if they're all odd. But I can't do that because I can't add 2 of these to get 16. Right, which leaves 21. Perfect. And I think it was Karsten earlier who gave it a solution. So Karsten says with 21, you can have 15 for boys and then the rest of the numbers added up for girls. Again, trying that, 81 minus 21 leaves us 60. 60 divided by 4 is 15 boys, which means there are 45 girls. So if I remove the group of 21, that means the group of 15 is boys. And then we just have to double check it, as it should. 9, 17, and 19 have to add up to 45. And they do. So we definitely know that it's a solution that works. Kind of has to, because we proved that all the other ones are wrong. But in any ways, we know that this works. So we remove that 21 team.
Nice. One other way I saw was, instead of looking at them mod 4, I looked at them mod 3. So we want to find, remember, look at the problem. We want to find 3 numbers that basically add up to 3 times one of the other numbers. But if it's 3 times one of the other numbers, then that has to be divisible by 3. So we basically want 3 numbers that when added up are divisible by 3. So let's look at each number mod 3. 9 is a multiple of 3. 15 is a multiple of 3. And 21 is a multiple of 3. 17 is 1 less than a multiple of 3. And 19, it's kind of hard to see the 19, but 19 is 1 more than a multiple of 3. So if your group of 3 numbers that were supposed to add up to a multiple of 3 had only a 17 in it and not the 19, or only the 19 in it and not the 17, then it would have all multiples of 3 except for one number, and that makes it automatically not a multiple of 3. So either the 3 numbers, among the 3 numbers, none of them are 17 or 19, or both of them are included. Let's try and see what happens if neither of them are included. Then that means it would have to be 9 plus 15 plus 21. And if we add them up, that's 24 plus 21, that equals 45. And that is 3 times 15. But we already used the 15. What this is saying is the teams with 9, 15, and 21 haven't started, and so has the team with 15, but we use the team with 15 twice. That's not going to work. So now, because we know that doesn't work, the only other option is for both 17 and 19 to be included. One of them is 1 less than a multiple of 3, one of them is 1 more. Those basically cancel out, and their sum is 36, which is a multiple of 3. And then we'll add 1 more multiple of 3 to that and see what happens. Let's try adding 9 first. That's 36 plus 9, which is 45. And that is 3 times 15. And that works. The one that wasn't used is 21, and that's our answer. If we want to be extra sure, we can try the other options and see if they don't work. So the other option is 17 plus 19 plus 15. That is actually, with this one, we can see pretty clearly that all the numbers average to 17, because 19 is 2 more than 17 and 15 is 2 less than 17. So clearly this would be 3 times 17. But this can't work again because there's a 17 here and a 17 here. And we use the 17 twice. That's no good. And the final option, 17 plus 19 plus 21, is a similar token. These average to 19 because this is 2 less than 19 and this is 2 more than 19. So this would be 3 times 19. But we already used the 19. It's the same thing again. So we showed that this can't work. We showed that adding in 21 can't work. Adding in 15 can't work. So the only possibility is adding in 9, which is 3 times 15. And so that's another way we can see that the answer is 21.
Yeah, so a bunch of different ways to look at the problem, which is really cool. So it just goes to show you there's always different solutions. And it looks like next we have a nice diagram.
So this diagram is asking us, what's the sum of the measure of the 6 marked angles in the picture? Is it 360, 900, 1080, 1120, or 1440? And I can immediately see that it's not 360 because these marked angles, all of them are really big. Like these two are both more than 180. And so them individually already add up to more than 360. So we know already that that is way off from the true answer. One thing I can see is, let's try adding in some angles. So if we included this, if we included these angles I have in yellow, let's try to find the sum of the shaded angles and the yellow angles. So this one is 180. This one is another 360. So far we're at 180 plus 360. This one is another 360. This one's another 360. This one's another 360. And finally, this is another 180. So if we wanted to add all of them up, then this is 5 times 360, which is 1800. So the shaded plus the yellow is 1800. So let's write that down so we don't forget. Shaded plus yellow equals 1800. Now, let's try to find the yellow angles. If we find the yellow angles, then we can deduce what the shaded angles are. The yellow angles are inside of a polygon. Let's see how many sides that polygon has. There's 1, 2, 3, 4, 5, 6. There are 6 sides to this polygon, and the sum of the interior angles of a polygon we can figure out with, we know that a triangle is 180, a square is 360, and then each additional side you add adds another 180. That's a terrible pentagon, but a pentagon is 540 and a hexagon is 720. The formula would be 180 times n minus 2. Yeah, great job, Matt. So we know that the yellow angles, because they're just the interior angles of a hexagon, they sum to 720. So substituting into our original expression, shaded plus yellow equals 1800. So shaded plus 720 equals 1800. And yeah, exactly, Karsten, you got it. 1800 minus 720 is 1080. So that's our answer. But I saw in chat that a lot of you had a different approach to this problem. So Eddie, do you want to show us the other approach?
Absolutely. So you guys are doing really cool stuff in chat. And so, for example, Alex said you could draw lines parallel to every side at the vertex. So basically, instead of, I'm going to draw it a little over here. So basically looking at, for example, drawing a line across here, or actually, is this what you mean, Alex? I'm not sure. I guess going vertically, because that way you can split it up to, oops, that did not go through the right point. But basically, for example, by drawing, pretend that they're exactly vertical. Like pretend that these are very nice and drawn. Like this angle and those angles are, oh, they are parallel to vertical sides. Cool. So looking at this one right here, this portion of the Pac-Man angle and this portion of the acute angle, they add together to 180 because they're, they're like alternate interior and alternate, I think that's what it's called, right? Sorry, the same side interior. I don't know what the essential names are, but basically, since this angle is the same as the blue one right here, that's going to add up to 180. And so you just keep going for all the angles. Like you would draw another one here where it would be these two here, this one and this one are supplementary. And actually, yeah, this is also a really quick solution, I think, as well. So keep in mind that because these are perfectly straight, that's a 90-degree angle. So that's 90. And then what's nice is that every space in between these vertical lines create exactly one pair of supplementary angles. So actually, this is a really cool solution. I love it. All right. And honestly, I technically didn't even need to label the fact that that was 90 because, oh no, I keep straying to the right. This 90 combined with this 90 is going to be 180 as well. So literally what we do is if I mark every space in red, that's gonna be one 180. That's gonna be two 180s, three 180s. Oh no, that's terrible. Let's try it again. Three 180s, then we have four 180s, five, and then these two 90s combined to make six. So 6 times 180 gives you 1080, and that's exactly the same answer. So that's really cool. I was a little perplexed earlier about the fact that I thought the formula only worked on convex interior. I thought that this very, very convex angle, convex, concave, this very like complex angle would ruin the fact that a hexagon sums to 720. But there you can still draw four triangles in it, and that's where it comes from. So basically, we wanted to subtract out all the yellow angles, right? And Vincent had them over here. And one way to look at that is just divide everything in triangles. So with my four triangles, 1, 2, 3, 4, the sum of the interior angles of all the triangles match exactly the interior angles of all the yellow angles. So I forgot to draw these in. So the yellow angles cover every single interior angle of the four triangles combined. So by subtracting out the four triangles, which we know are each 180, bam, that's also the same thing, 720 degrees. And be careful when you're drawing the triangles. Like for example, if I instead said, drew a triangle, I don't know, like going this way and like, I don't know, this way, what that's gonna do is create a triangle where the angles make up some angle here instead of the yellow ones. So that's not what we want, which is why whenever I draw the triangles, I make sure that it's going from some vertex to another vertex in the diagram. So that's how I got this one here.
Nice. Are we all ready to move on to the next problem?
Sounds good. Okie doke. So I believe we have only 3 more, so we're doing good. Let's check what this one has. The numbers A, B, and C oops, I am upside down now. Oh, solve the problems. All right, the numbers A, B, and C satisfy A plus B plus C equals 0 and ABC equals 78. What is the value of A times B, A plus B times B plus C times C plus A? So right away, we have two equations, but three variables. So we probably aren't solving for ABC. We have to manipulate these equations some way such that they give me exactly what's going on here. So start by factoring 78. Wait a minute, are they supposed to be integers? Because this is a really good strategy if they are integers. But I'm not entirely sure if they're integers. Because what Matt's saying is if we factor 78, so 78 is divisible by 2, and that's 39, and that's divisible by 3. So we know it's 2 times 3 times 13. The problem is, though, I'm not entirely sure. Yeah, I don't see a possibility where you can make some of them negative such that they add to 0. So Helen says maybe expand the product. Let's try that. So the fact that after you expand, you get a squared plus b squared plus c squared plus ab plus b. Sorry. If you were to actually do the messy expansion, you'd get something like this. I'll save you guys that part. So we know it looks like this after expanding. Alex had another idea, said, can write the product as 0. Okay. You had a really good idea, Alex. So I'm going to rephrase that by saying, we're going to make a polynomial. Well, this problem doesn't talk about polynomials at all, right? So why would we do that? And by the way, sorry, I want to finish this thought first. So how would we manipulate, the facts that are given to get this? Since this is a squared plus b squared plus c squared, my first instinct is to like square this one here. But, oh wait, did I do this right? I don't think I expanded this right. I'm trying to think. This is not right.
Plus b times b plus c times c plus a. So you'd have basically all 8 possible choices. So we could have all the first ones. No, they would not be added. They would be multiplied. A, B, C. We could have the first one, then the first one, then the second one, plus a squared b. We could have the first one, the second one, then the first one. That's AC squared. And then if we keep going for all 8 of them, we'll get 2ABC, because we can get that from either choosing all of the first ones or all of the last ones, plus 2AB squared plus 2AC squared plus 2BC squared. And that looks pretty ugly, and I don't think that this will help us solve the problem, although it is a good thing to expand it out and see what you get, because you never know what you might get from expanding out.
Yeah, so lesson learned, do the dirty work. It saves you from getting it wrong. So yeah, what I wrote here in Lime is a plus b plus c squared. And what Vincent had on screen, I think there is a way to manipulate the two facts that they give such that you get what Vincent had on screen, but there is an easier way to do it. And so this whole thing about Vietas, right? Arjun says Vietas in chat. So the reason why we look at Vietas is what's a ringer for Vietas is the fact that, so for any cubic, we're talking about cubics now. So I'm going to do it this way. So I'm going to make the colors let's hope I spaced this correctly. So we have these coefficients, right? Just standard, you know what? It's a third degree polynomial. And what's really nice is that if the roots, wait, I've messed up. I'm going to not call them A, B, C, D because that makes it not fun. Let's call them, all right, I'm going to be really lame and just call them all R. Actually, wait, what variables do you guys want? They just don't, the reason why I don't want them to be A, B, C, D is because we used A, B, C here. What variables do we want to use? How about P, Q, R, S? How about that? All right, P, so if we say that the coefficients are P, Q, R, S, P, okay, yeah, I know you wanted to do R1, R2, but the reason why I kind of don't want to do R1, R2 is the fact that R is supposed to be the roots, and this is very much not the roots. Okay, so PQRS, what's really nice about Vietas is that it tells us the sum of the roots. Okay, let's just say it has roots A, B, C. So if this polynomial has roots A, B, C, which means if I put f of A, it'll give me 0. F of B, it'll give me 0. That means if it has roots a, b, c, I can write this as x minus a times x minus b times x minus c. That's the definition of a polynomial. You can factor it into its roots. Another thing that's nice is what's called Vietas. So Vietas formulas tell us that the sum of the roots, so in other words, a plus b plus c, is in this case negative q divided by p. And then it tells us that if you multiply them in pairs and then add them, that's going to be the same as positive the second coefficient over the leading coefficient. And then you can actually verify this just by expanding it. It's not that hard to prove. Literally just multiply out and you'll see exactly why. And this gives us S over P. And so this is the reason why we think about Vietas, because well, if we're given ABC, that's that. And if we're given A plus B plus C, that's this one right here. And we're told this is 0, right? So if this is 0, that means Q has to be 0. So that's already a big hint, because the only way for a fraction to be 0 is the numerator is 0. So right away, good catch, guys. We can just completely remove the x squared term because it's 0. So now we have P plus Px cubed plus Rx plus S. And the thing is that, oh wait, the most likely answer is none of the above because there are infinite numbers that apply to it. Might be so. Is it overthinking? All right. I think if you plug in, for example, plug in 0, I think you get an S, right? So f of 0, which means, sorry, not f of 0. Okay, sorry, I'm thinking about plugging in a root. If you plug in f of 0, that gives you, okay, wait, I'm going to move this Vietas to the side right now over here. If I look at f of 0 at the top, that's going to give me just S because everything else gets multiplied to 0. If I plug in f of 0 to the bottom, which is the exact same thing, I get that this is equal to negative ABC, which is equal to 78. So we know that S is equal to negative 78. Wait, sorry. This is negative 78. So that means S is negative 78. So now we're down to, actually I'll make this in green. Now we're down to P and an R. Wait, this proves that P is 1, yeah? Because the product is, does it work like that? Oh wait, sorry, I didn't multiply this by P, that's why. Oops. So we don't know if exactly if it's 78. What is value A plus B? Is there a way to plug in something that you get exactly A plus B times B plus C times C plus A?
I don't see a way to do it with Vietas because whatever you plug in for X, like let's say you plug in A for X, then the X minus A can become 0. Same thing if you plug in B for X, and same thing if you plug in C for X. What if you plugged in A plus B plus C? If you plugged in A plus B plus C for X, then I think that gives you it. A plus B plus C minus A, that's B plus C, and so on. So if we could somehow plug in A plus B plus C, then we could solve it using Vietas.
That is very smart. So we basically have two ways to write the equation, right? And the thing I forgot to add earlier is that whatever the leading coefficient is, you have to put that here. So like X times A, X minus A times X minus B times X minus C gives you a leading coefficient of 1. But it's not 1. We have to multiply by P. And what Vincent's saying is that plugging in something for X, so if I say f of X, no matter what I plug in, it's going to be really hard to get an A plus B times B plus C times C plus A. But what if I plug in A plus B plus C? So Vincent, big brain move. What if we do this? So that means I'm plugging in A plus B plus C for every time I see X. So that's exactly so like I would do A plus B plus C because that's X. Right, let me do this in blue. So A plus B plus C minus A times A plus B plus C minus B times A plus B plus C minus C, which means I'm getting exactly A plus B times B plus C, times B plus C times A plus C, which is exactly what we're looking for. Which means now the question is, what's f of A plus B plus C? Do you guys see a shortcut?
We know that A plus B plus C is 0 because that's in the problem. So it just becomes f of 0.
Yes. This is crazy, right? F of A plus B plus C is really nice because that's just 0. And so now the biggest thing is, well, what's f of 0? And if we plug it back in here, that's just that last coefficient. And wait a minute. Does it tell you that the leading coefficient is, I forgot to add the leading coefficient here. That's what the problem is. So don't forget about the leading coefficient. This is P times what we want. And f of 0 is going to give us just S. So I guess you can just do all of this without thinking about the leading coefficient whatsoever. But it doesn't say that the leading coefficient is 1, so you can't just assume it. And we know that ABC equals 78 is equal to the last coefficient over P.
Well, it would be the negative of the last coefficient over P, right?
Thank you. Thank you very much. So don't forget to keep it negative. And so we know that f of 0 describes P times what we want. So equals S, which is equal to P times what we want. P times our answer. Actually, let me keep P in red. P times our answer. So since S is equal to P times ABC, which we know is, negative P times ABC, which we know is 78. So S is equal to negative P times ABC. First of all, now we're saying negative P times ABC equals P times the answer. So we cross out both P's, which means negative ABC is equal to the answer. So negative APC is equal to negative 78, which is none of the above. Did they really make us do all of that to say none of the above?
I forgot who said it, but whoever put in chat that none of the above was the most likely answer, you were probably onto something. It is 9 o'clock, but we still have a couple more problems, so let's try to finish them off. Let's see what we have next. Yes, the answer was none of the above. The smaller square in the picture has an area of 16, and the gray triangle has an area of 1. What is the area of the larger square? So the first thing that I want to figure out is, what is the larger square? It's not immediately obvious which square is larger, but I can look at this triangle right here in the bottom. And since this is a square, this is the right triangle. And the hypotenuse of the right triangle must have a greater length than the leg of a right triangle. The hypotenuse is the side length of this square, and the leg is the side length of this square. And so because the hypotenuse is longer, then this square has the larger area. So we know that the bottom right square is the smaller square, and so that one has an area of 16. And so each side would have length 4. So this would be length 4, and this would be length 4. We are also given that the gray triangle has an area of 1. So let's see how we could potentially use this information. When we're given area, one thing that is often useful is to reduce it to area equals 1/2 times the base times the height. So maybe we can use this to try to deduce information about the base or the height. Or maybe we can look at it differently, because what we also know is, actually that doesn't really work, but we still know these side lengths, and we still know this is the area. Arjun says this screams similar triangles, and let's see if we can find any similar triangles here. So let's call this angle A, then let's call this angle B, and we know that A plus B have to equal 90, because the sum of the angles of a triangle is 180, and this angle is 90, so A plus B have to equal 90. So if this angle, this angle is also 90 because it's part of a square. So now we can deduce what this angle is. It would have to be A, because we know that A plus B equals 90, so that works. But how we would deduce it is A plus 90 plus B have to equal 180. They're all part of this line. So if A plus 90 plus B equals 180, then we can subtract 90 from both sides, and we get A plus B equals 90. And so we get that this would be A. And it was kind of confusing because I used the variable A in multiple places, but hopefully you see why this has to be A. And because this is the right angle, this is also B. Then this would be 180 minus B, because these two sum to 180. And so this would also be B, because these two sum to 180. And so now we've basically angle chased our way to finding this angle is B. Now let's try the other side. We know that this angle is 90 degrees, but actually the more useful angle to look at might be this one. This one is 90 minus A, because this angle is 90. This is 90 minus A, and we know that 90 minus A is just B. So if this angle is B, and this angle is 90, then this angle has to be 90 minus B, which is A. And since this is a right angle, then this angle has to be B. So we're seeing a lot of similar stuff here. We've got this triangle with angles A and B, this triangle with A and B. So we still haven't figured out how to make use of the triangle with area 1. So let's look at that. Can we deduce some of its angles? Well, we can. We know that this angle is B and this total angle is 90. So what would this angle be? Well, it would have to be 90 minus B. So this angle is A. Now let's look at this angle. If we know that this angle kind of looks kind of weird. It's a lot smaller than the other ones, and it doesn't seem like we have enough progress to try to figure out that angle, and it doesn't really seem that useful anyways. But if we know that this angle is A, what if I try, let's erase stuff to get this out of the way. Let's see if dropping this altitude would give us something. Because that would be the height of this triangle with area 1. And now we might be getting somewhere. If this angle is A, then this angle would have to be B, because this angle is 90, and so it's similar to the gazillion other triangles we found. And actually, it's congruent to the other triangles we found, because we can look at, it's not congruent to all of them, but it is congruent to some of them, and that might be useful. But regardless of that, this triangle looks super useful to us, and let's see if we can try to find the base and the height, because that will give us the area, and if we know 2 ways to get to the area, then that will allow us to solve the problem. So this triangle that I've outlined in yellow is similar to all of these triangles we found. And so let's see if we can put that to good use. We know that we already know that this is the height. So let's see if we can try to find the height somewhere else. So we know that this long side equals this long side, because they're part of the same square. So yeah, this triangle would be congruent to the bottom one. So because this triangle at the top is congruent to one at the bottom, as Luke pointed out, and we know that this side has length 4, then we also know that between this point and this point, let's switch to a different color because it's starting to get cluttered. We know that this length also has length 4. And if we know this length and we know the area, now can we find the height? Yes, we can. We have enough information now. We know that the area is 1/2 base times height. And we know the area is 1, the base is 4, and the height we don't know yet. So 1/2 times 4 is 2. 1 equals 2 times the height. That means that the height has to be 1/2. Actually, we found the area of the wrong triangle here. We found the area of this big triangle, not the area of the small triangle. So we can't quite see what that area is. The base should actually be this. Yeah, good catch, Luke. So our base is this, and so is our height actually. So are these triangles congruent? Let's double check that these triangles are actually congruent. So we know that this length is the same as this length. Now let's look at this triangle on the left. The triangle on the left has this hypotenuse, and that's the same side length because it is part of the same square. So it is in fact congruent. And so whatever this height is and whatever this base is are in fact the same. So now we know that we can try to use the area equals base times height formula, but we already know that the base equals the height. So we can write area, which is 1. Area equals 1/2 base times height. The area is 1. And so 1 equals 1/2 times the base times the height, which is also the base. So it's really 1 equals 1/2 times the base squared. We'll multiply both sides by 2. 2 equals the base squared. And so the base is the square root of 2. And so is the height. Let's try to look at what we were originally trying to find. What is the area of the larger square? So what information can we use to try to find the area of the larger square? Well, the side length would certainly be useful, because if we knew the side length, we could just square that and we would be able to find its area. Oh, Matt says, does the area of the green triangle really equal 1? And yeah, it does not equal 1. The area of the green triangle is actually greater than 1. It's the gray triangle that has an area of 1. And that's why we wanted to multiply this base by this height, not the entire green triangle. And that's why we were able to say the base equals the height, and we were able to find what the base was. And it's the square root of 2. And so now we can use the Pythagorean theorem. We know that this is the square root of 2 because it's congruent to the other triangles in the diagram. So it corresponds to this side. This one is the square root of 2. This one is 4. And now let's find the hypotenuse. A squared plus b squared equals c squared. So we have 4 squared plus the square root of 2 squared equals c squared. 4 squared plus the square root of 2 squared equals c squared, where we're setting this length to be c. So 4 squared is 16. The square root of 2 squared is just 2, and that's c squared. So 18 equals c squared. Now hold on. The area of a square is its side length squared. And c squared, that's just the side length of the larger square squared. So we actually already have our answer. The area of the largest square is 18. It took us a while, but we got there in the end.
That's kind of crazy. I honestly was really lost on this problem, but way to go, guys, in chat for figuring it out. Honestly, if we kind of look back, all that work, it's all geometry I find is all about knowing where to look. Because basically, as a review of what we did, all it boiled down to is finding that this triangle and this triangle they're congruent to each other because the hypotenuse are both the side length of the larger square and they have the same angles. And then from there, because they're congruent, the base of this, which happens to be the base of the gray triangle, as well as the base of this green triangle, it's still the pink length, but this is also the height of the gray triangle. So half base times height, which is half x squared, is equal to 1. X squared is 2. And then because this side length is 4, this side length is also 4. And then bam, Pythagorean theorem. You just add this up. So I guess if you get really lucky and find that right away, you can do this problem in like a minute. But it's just so hard to find stuff like that. So I'm really glad that we went through the entire process. You guys and Vincent basically magically found it through experimentation. And I think that's what geometry is like. So that's really cool.
Yeah, solving geometry is like you're lost in the woods and you need to find a way out. And good job, guys. We were able to find the way out. So now let's move on from geo to another type of problem. How many 5-digit positive numbers have the product of their digits equal to 1,000? So Eddie, how do we do that?
All right. So this time, because we're talking about 5-digit numbers, they are integers, and that's really helpful. So we know 5, basically it's saying 5 integers, 1 through 9, well, technically 0 through 9, but obviously there can't be a 0 in there, otherwise the product would be 0. So digits 1 through 9, they multiply together to equal 1,000. So right away, 1,000 is a big number, so that's giving me pretty good hope. But absolutely, do what Karsten did. Start by factoring, because we're looking for 1,000 in terms of the product of a bunch of numbers. So absolutely, start by factoring. So we know that this goes into a bunch of 2s and 5s. So 2 cubed times 5 cubed, and bam, that's how we want to do it. So this is equal to 2 cubed times 5 cubed. All right, it's getting a little jumbled up in there. And now we want to make it so that a 5-digit integer, a 5-digit positive number. So we want to if I were to multiply 2 times 2 times 2, sorry, 2 times 2 times 2 times 5 times 5 times 5, that's 6 digits, which means we have to combine at least one of them such that we have 5 digits. But here's the thing. The number, yes, Alex says the number has to have 3 5s, because guess what? If I try to combine the 5s with a 2, 5 times 2 is 10. That's already way too big. So I can't do any of that, which means the only way I can, take it from 6 digits to 5 digits is by combining the 2s. What I mean by combining the 2s is like, instead of 2 times 2 times 2, I would say 2 times 4. So one possible way is to arrange 2, 4, 5, 5, 5, 5, 5. So this is a possibility. What if I combine these 2s, right? What if I combine these 2s? Well, that would be a 4, 2, 5, 5, 5. That's just basically the same thing here. So we leave the 5s alone because they get too big if we combine anything. Is there another way to combine them actually? So one way is to combine 2 of the 2s, but is there another way to make it so that we still stay within the 1 through 9? It's still a 1-digit number. Exactly, what you guys have in chat. So 81555 and 18555, same thing. So if we combine all 3 2s, we can say 1 times 8, and it's still 5 digits, and they're all 1-digit numbers. So all numbers are in the form of a 2, a 4, and 3 5s, or a 1 and an 8 and 3 5s. Now it's just down to ordering them. So now the question becomes, how many ways are there arranged? 2, 4, 5, 5, 5, and then 1, 8, 5, 5, 5. So normally the way we arrange 5 people is say there's 5 times 4 times 3 times 2 times 1. 5 factorial ways to arrange the people, yeah? Except now they're not all different people. So we start with 5 factorial, but now here's the problem. I want to say I arrange 2 people and then 3 identical sheep. So I have a person A, B, and then 3 identical sheep. How does that work? Well, whenever we rearrange 5 people like that, I'm gonna make this. I'm gonna label the C's C1, C2, C3. So they all look the same to us. They're all C. But for example, if I had A, B, say C, 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 but it's like C2, C1, C3, it looks the same to us, but we technically flopped around the 2, right? So if they're all all identical sheep, for example, they look the same, but we actually swapped them around. So these 2 are the same, but we counted them differently in this 5 factorial. The 5s are indistinguishable, right? The C's are indistinguishable in this case. So how many ways are there to account for the identical sheep or the 5s? How many ways are there to divide it out? So basically what I'm saying is, if I said 2, 4, 5, 5, 5, we could arrange them by saying there's 5 ways to put the first number, and 4 ways to put the second number, 3 ways to put the third number. But the fact that I can rearrange the 5s and have nothing change visually, there's 3 ways to do that. Sorry, 3 factorial ways to do that, right? There's 3 factorial ways to arrange the 3 5s such that they look the exact same. Which means no matter what arrangements it's in, so like say it was like this instead, I'm counting it 3 factorial or 6 times. So I could have said that, or like that. They all look the same. Which means instead of 5 factorial, I needed to divide out 3 factorial. Which means this is equal to 5 times 4, which is 20. The big idea is I'm overcounting every time I say 5 factorial. I'm counting 2, 4, 5, 5, 5, and a 2, 4, 5, 5, 5, and a 2, 4, 5, 5, 5. How many times am I overcounting that? The same way I can rearrange the 5s. I'm overcounting this 2, 4, 5, 5, 5 6 times because there's 6 ways to rearrange the 5s such that they look the exact same. So there's 20 ways, 20 different ways, and that's just for the 2, 4, 5, 5, 5 case. But if we look at the 1, 8, 5, 5, 5 case, it's still the same thing, 3 identical objects and 2 different objects. So both of them are going to be 20. Which means, bam, 20 plus 20, our answer is 40.
Nice. Another way you could have thought about it to get 20 ways is you arrive at the two cases, 24555 and 18555 the same way, but now you ask yourself, I have 5 positions. Where do I want to put the 2? I could put it here, 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 or here. And there's 5 ways for me to do that. And then now I ask myself, where should I put the 4? I could put it here, 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 or here. And that's 4 ways, 4 possibilities. And so I'll multiply that by 4 because for every way the 2 could have been, there are 4 ways that branch off of that I could put the 4. But then the 5s, they just fill in and there's no freedom. We have to fill them in with 5s. So the total number of ways is just 5 times 4. That's 20. And then likewise, it's the same process with the 1 and the 8. Another 20 ways. And by the same token, we just add them and we would get 40.
Cool. Bunch of different ways to look at the problem as always. So that's always really nice, the fact that you can look at them in so different ways. Speaking of different ways to look at it, I know this is one from really far back, but I just wanted to add another note. So another way to look at this problem, I realized I found this after we did everything. So if you look at it visually, it actually, I think it makes it easier to see. I don't know if it's necessarily faster, but I kind of like it visually. So for example, multiplying by 10, so it's a number. Let's represent the number by a bar. If we multiplied it by 1/10, we're just taking 1/10 of it. So that's just this section. And you're saying that's the same thing. So hold up. This is just 1/10 of the bar. You're saying this is the same thing as subtracting 1/10, which means the value of everything I cut off is 1/10, all of this here. Wait, this is also 9/10 of the bar, right? Because we cut off, we had 1/10, that rest is 9/10. So you're saying 9/10 of the bar is exactly equal to the 1/10 we cut off. And here it's really easy to see that the number is 1/9. But it's basically the same thing, just visually. So another way to look at it. All right. It's a little past 9, a lot past 9, but thanks to everybody for sticking along all the way to the end. I need to clear out this extra stuff. But as always, thanks for joining us. And you can always catch us at other live solves in the future.
The next level 9 to 10 live solve is going to be on March 10th at 8 p.m. Eastern time. And if you're interested, you can scan the QR codes on my screen or go to the links. Thanks for joining us today and have a good night.
Yes. Way to go, everybody. Thanks for coming. Hope to see you guys soon. All right. If anybody has other questions as well, I have time. I'm down to chill if you want. I don't know if you have places to go, Vincent. But
now I also have time.
Awesome. I really like that geometry problem. Normally I'm not a fan of geometry, but the fact that all the numbers magically work out. It was like, why are they giving me just that little gray triangle? But I understand now. That was pretty cool.
My diagram is one of the diagrams of all time.
But I feel like that's just what happens when you do geometry.
Yeah.
And then magically you land out what you're supposed to do. So that's cool. It really was a life solve.
Yeah, geometry is frustrating until you get to the end and it's all worth it. Every step of the way, it's all worth it when you finally solve it. For me.
Yeah, it's pretty satisfying, especially like, I don't know, when you got the right answer, I was like, wow, that was really complicated. But then I did a recap and I was like, wait, it was just that like 2-3 steps, but it's just really hard to see. It's not what you see right away.
Yeah. There's a bunch of, if you think of geometry as navigating a forest, there were so many dead ends there, but we were able to make it out.
Yep. I do really like the forest analogy.
Yeah. Another one of the problems that we also found was kind of like a forest was this one.
Yes.
Where we used a bunch of complicated techniques, but what our solution ended up being was actually there's an even simpler version of our solution.
Oh.
We want to find a plus b times b plus c times c plus a. Let's rewrite it as a plus b plus c minus c times b plus c plus a minus a times c plus a plus b minus b. But hold on, a plus b plus c is 0. So this term is just negative c. B plus c plus a is 0. So this term is negative a. And c plus a plus b is 0. So this term is negative b. And therefore, we have negative CAB. We know that this equals negative 78. And so the value of this expression is negative 78. And that's how you would get none of the above.
That was so fast. That takes literally 4 lines of work, 5 lines of work. Wow.
And I think some of you actually saw this. I saw
Yeah.
something similar to this in chat.
I
So
wasn't
if you
able to
found it,
react fast
nice
enough.
job, guys.
Yeah, that was really cool. I was trying to process what's going on, which is why I wrote the f of x equals x minus whatever. But I never ended up getting led to that, so that's unfortunate. But yeah, that's really cool that you guys saw it.
Yeah, it wouldn't be a Professor Lowe problem without an easy way to do it and a hard way to do it. And with this one, we definitely picked the hard way to do it. But we still got there in the end.
Pretty accurate though. I feel like so many times it's like in hindsight, after you finish the competition, you're like, wow, that was not hard. But I remember this year I was telling myself, I'm like, you know, when you're looking at the solutions in the future, just tell yourself that during the test, you thought it was hard. So don't face palm or anything. Like during the test, you could not solve it. So don't like, you know, beat yourself up for being like, oh, it's super easy. Like it was hard.
Yeah, I guess you could apply the lost in a forest analogy too. If someone tells you how to get out, then obviously you walk this way and then follow that way. Obviously you go that way. But if someone doesn't tell you, you're just lost in the woods.
Exactly. Actually, that's really fun. It's like in a maze, you have no idea if you're right next to the exit or not. Oh,
And as you get more experience, you'll start to be able to find your way out of the maze faster, but there will still be these moments, especially when dealing with harder problems, where in hindsight, it looks super simple, but the process is quite long-winded.
yeah. All about the process. All right. I think that experience part is definitely key though. It's the only way you get to see these faster is when you start doing these problems more and more. But thinking and figuring it out is half the fun. Or maybe honestly most of the fun, so.
Well, yeah, it's no fun if you just Google the answer.
Yeah. Sometimes it blows your mind though. It's just like, wow. I did not think of that. Alrighty. Wrapping up soon. Any final questions from anybody?